Okay, so we want to solve this exponential equation. The problem is it's an exponential, right? That my variable is hidden up here in the exponent, and then I don't have access to my variable. This is the whole reason that we had to introduce inverse functions, and then the particular inverse function of a logarithm for our exponentials, so that we could have a way to access this variable in the exponent. The whole reason we had to build up this entire chapter's worth of information is so that we can find a way to solve this equation that doesn't require just plotting the thing on our calculator and looking for the intersection of two lines. So how am I going to do that? I still have kind of those basic three rules from my logarithms, right? I have my arbitrary base log, where I'm multiplying my arguments, and that's my same base log of argument 1 plus the same base log of argument 2, right? So I'm going to do a natural log just because it's easier and quicker to write down. And then 2 would be my log of an argument raised to a power is the same thing as that power is the coefficient of that log of my argument. And then 3 is my division, right? So I have the natural log of 1 divided by another, one value divided by another. And so it'll be the natural log of the first minus the natural log of the second. And so of those 3 rules, this middle rule looks like it's going to let me have access to this exponent, right? Because it's going to let me pull that exponent down and turn it into coefficient. The problem is that 2 to the x would have to be the argument of the logarithm for that to work. Well, that's only a problem because I haven't run both sides of this equation through a logarithm. I can do that. I can run both sides of this equation through the natural log of x and end up with the natural log of 2 to the x equals the natural log of 33. And now I'm going to have x ln of 2 equals ln of 33. And now I'm just going to divide both sides by the natural log of 2. And I'm going to have x equals the natural log of 33 divided by the natural log of 2. X equals ln 33 divided by ln of 2. And I'll get 5.04 approximately for my value. And if I want to check that, what do? Well, I go back here and type in 2 to the x for one function. I type in 33 for my second function. I don't particularly care about my window, except that I probably ought to be able to see the 33 there, right? And then I look for the intersection of those two, and the intersection tells me that the x value for that intersection is 5.04, which is exactly what I got when I solved, or approximately what I got when I solved the equation. Okay, well, that was a relatively straightforward equation. Let's look at one that might not be quite so simple. What would I do if I had something like let's do 3 to the x equals 2 to the x minus 1. How would I solve that? Well, I have the same problem. My variable's in my exponent. I don't have access to my variable. I need my variable down out of the exponent. I have the same tools and the same solution. That second equation will allow me to pull my exponent down and turn it into a coefficient. But for that to work, this needs to be in the argument of a logarithm. And so I need to run both sides of this equation through a logarithm. And so what I'll have is natural log of 3 to the x equals natural log of 2 to the x minus 1. Okay, well, now I can rewrite this. X ln of 3 equals x minus 1. That's one number. That one number is times the natural log of 2 here. Now I've got to figure out how to solve that for x. And while it's not the most straightforward algebra, it is at this point just algebra solution as we've done before. And so now I've got x ln of 3 equals, and I'm going to distribute that natural log through. I have x ln of 2, and then minus ln of 2, right? Because I distributed that to the negative 1 as well. And now I want to get everything involving x on one side and everything that doesn't have x on the other. And that means I got to subtract x ln of 2 to the other side of the equation. So minus x ln of 2 minus x ln of 2. Okay, and so that's going to give me x ln of 3 minus x ln of 2 equals negative ln of 2. Well, now I've got two terms involving x, so I can factor that x out in front. I can have this be x times ln of 3 minus ln of 2 equals negative ln of 2. Few things we can do here. We'll go ahead and divide both. Well, I'm going to rewrite this one more time before I do my division. I'm going to rewrite this as x. I'm going to use property 2, what have I labeled it? I've called it property 3 here, because this is a natural log minus another natural log, same base. This is a natural log minus another natural log, same base, and so that's going to be my property 3. And so I'm going to rewrite this as x ln of 3 halves equals negative ln of 2. Now, it's a little cleaner that way. Now I can divide both sides by that coefficient, natural log of 3 halves, natural log of 3 halves, and I get that x equals negative natural log of 2 over the natural log of 3 halves. And if I run that into a calculator, I have the natural log negative natural log of 2 divided by the natural log of 3 halves. We get negative 1.71 approximately. Okay, and if I wanted to test that, how could I test that? Well, let's go back to our original equation, our 3 to the x and our 2 to the x minus 1. And I would graph those two, and I would zoom in, try to find visually the intersection between the two, and then numerically I'd find the intersection between the two, and that 1.71, negative 1.71, looks to be the solution. So it's a good way to quickly check our work and make sure that we've gotten the right answer. Hope that helps us with solving exponential equations. We have to use a logarithm to then get the variable out of the exponent.